Hi everybody, welcome to the last video in pre-calculus section 11.4 Mathematical Induction. So this is kind of a strange way to end pre-calculus. So mathematical induction is a method of proving something. So the proof is this. The picture, I couldn't find any better demonstration than this. Think about the domino number from 1 indefinitely increasing from 1. If the first one falls on the second and then fall on the next one, meaning that if we know that at any point when the domino falls, if one of them falls, the next one will have to fall as well, right? And then we starting, the first one is falling, then everything will fall, right? So we just need two things to prove that everything falls. The first one is true, and then if one of them is true, the next one is true. So that is the principle of mathematical induction. We know the first one, it must be true, and then we know that if somehow we can show that if it is true on this step, it will be true for the next step as well, then it will be true for everything. That is the inducing, or the what we call the mathematical induction. So what we prove is this. First, we show that it is true for number 1. Actually, it can be true for any number, any natural numbers. So we start with that. And then next, so first we're going to show that it is true for 1. And next, we assume that it is true for k. And then we assume that, and then we will prove, assume, this is only assume, true for k. But we need to prove that it is true for k plus 1. With that, if we know that it goes from k to k plus 1 is true, when we know 1 is true, and we know that, of course, 2 is also true, and if 2 is true, it will true for 3, and then true for 4, and then just keep going. So we need this, and we need where to start. Right, so let's look at the first example here. Show that this statement is true for all natural numbers n. So there will be 3 steps. First, show that it is true for n equal to 1. Right, for n equal to 1, the left hand side is equal to what? Just 1, right? And the right hand side equal to 2 to the first minus 1 is equal to 1. So what we have is both of them equal to 1, so the left hand side equal to the right hand side. So that check. That's the first step. The next one is we assume, so we don't know that. So we assume that it is true for n equal to k. So I will write the statement. We know that this is true. And we assume that this is true. The next step is the proof. The statement is true for n equal to k plus 1. But what is the statement at k plus 1? So meaning that we need to prove I'm going to write this. Up to this point, sorry, this should be k. Right, I will write this, but up to when n equal to k plus 1, so I'm going to put in here k plus 1 for n, right? On the right hand side, 2 to the k plus 1 right, so we need to prove that. So how do we prove that? Now notice that, and I'll focus on the left hand side here of both of those. What we actually have is just the power will be 2 to the 0 power to 2 to the k minus 1. This is 2 to the 0 power to 2 to the k. So this statement compared to that, we have one more term. So I will do this. I will take the left hand side here equal to 1 plus 2 to the first, 2 to the second, all the way to, this is going to give us 2 to the k, right? But we're going to write that 2 to the k minus 1, and then next to the 2 to the k, right? Because in order to write this 2 to the k, we have to go from 1 to the k minus 1 and then to the k. But what we have is this statement is true, we assume it's true, which gives us 2 to the k minus 1. And then plus 2 to the k. 2 to the k plus 2 to the k is 2 times that. And that gives us 2 to the k plus 1 minus 1, which is the right hand side. So to recap, we just need to show that in the proof we really don't need to use that part. In the proof, I guarantee that we need to use this, the assumption that is true. And so we rewrite that and we have this, which is true. And all we do is we just add that term in, and that's what we have. So what we have here is the proof using mathematical induction. We need to check the first one though, so make sure that is true on the first one. And then what we need to do is the next one, if it is true, then we'll rewrite the left hand side using what we know in the second step, and we can write that. And that is complete proof. We have 3 steps like that. Right, let's look at one more example. I'm just going to do one more. I'm not going to do this one. This one is similar to the first one. So 3 statements. The first one, I show that this is true, that the statement is true for n equal to 1, right? For n equal to 1, the left hand side is equal to n equal to 1, right? 1 plus 1, 1 plus, so it's going to be for the right hand side, n is 1. So we have the left hand side greater than the right hand side, which is good. So that is the first step. The second step, we assume the statement is true for n equal to k, meaning that when n equal to k, 2 to the k plus 1 is going to be greater than k. Right? And we assume that it is true. And the proof is we need to prove the statement is true for n equal to k plus 1, meaning we need to prove that now we're going to put k plus 1 into this n, so we have 2 to the k plus 1 greater than k plus 1. By the way, that is 2 to the k plus 2, right? This is 2 to the k plus 2 greater than k plus 1. Right, now 2 times k plus 2, can I write that as 2 times 2 to k plus 1? And when I write like that, I can write 2 to the k plus 1 plus 2 to the k plus 1. Because if you have 2 times of something, it's just like that plus itself. And then what next is that we already have 2 to the k plus 1 is already greater than k. So equivalently, we need to show that 2 to the k plus 1 greater than 1. And that is easy, right? 2 to the k plus 1 is greater than k, and k is greater than 1. So since this one greater than k, this one greater than 1. So we have this one greater than k because of the assumption is true. And we have this one also greater than k, but k is greater than 1. So yes, so this is true. So what we have is that 2 to the k plus 1 greater than k and 2 to the k plus 1 greater than 1. So when we add them, this will be greater than that. So that is the proof. Of course, we can write this backward if we want to. But that's what we need to do. So mathematical induction depends on the type of problem. It could be completely different from problem to problem, but the principle is pretty simple. It will be true for a very small number, and then we assume that it is true for some number. All we need to show is that if at any number, if it is true, the next one is also true. In that case, if it is true for 1, induce it is true for 2, induce it is true for 3, and then so on for the rest of the natural numbers. So that is the principle of mathematical induction. But I just want to end the section here. And that's all I want to cover for pre-calculus for one last time. Thank you for watching.